In this video, we're going to look at two more examples for exponential and logarithmic equations. The first is doubling time. So we looked at half-life. Now we're looking at when things grow, doubling time. So similar to half-life, the doubling time is how long it's going to take for some quantity to double. And using the basic exponential equation that we worked with in the last examples with half-life, a doubling time would be doubling the original amount, which we call A. And again, canceling A. So we're really saying, how long does it take, oops, for B to the T to achieve a 2, so that we're multiplying by the original amount. Okay, so let's look at an example of where doubling time is useful. Now, it's kind of sad, but cancer cells increase. And they increase exponentially. So if we're looking at cancer growth, how long would it take for the number of cancer cells to double? So what we want to use or figure out here is what the growth rate is. Okay. So immediately we know that if cancer cells contained 300 cells last month and then grew to 360 cells this month, what is the growth rate? Okay, so if we're starting with 300 cells, we can make that our A. Okay, and if A is 300 in our equation, in 1 month, it grows to 360. So 360 equals 300 B to the 1. So B is 360 divided by 300, which I get 1.2. So there's B. So how long is it going to take to double? So if that's B, to double, just kind of referring to what we wrote above, right here, 2 equals B to the T. That's doubling time. How long does it take 1.2 to the T to equal 2? So I need to take the natural log of both sides, or log. Bring the T down. Divide both sides by the natural log of 1.2. So T equals natural log of 2 divided by the natural log of 1.2 in my calculator gives me 3.802. And that would be months. So here, we'll just say 3.8 months. Let me go ahead and give myself space to write that word. So in 3.8 months, the cancer cells has doubled. Wow, that's an aggressive cancer. And there you go. Okay, let's look at a different one. Use of a social networking site has been growing exponentially with the number of new members doubling every 5 months. Okay, so they're giving us the doubling time. If the current site has 120,000 users, use this trend, how many users will it have in 1 year? Okay, so following that trend in 1 year. So if our doubling time then is 5 months, I can find B by raising both sides to 1/5, not half. That's a 5. So I get 2 to the 1/5 comes out to 1.1487. I'll go at least 4 decimal places. All right, so there is my B. So how many users will the site have in a year? So I found B, and currently it has 120,000. So here, let me write my equation. So that's A. That's the current users growing at this rate. 1.487. How much is it going to have in a year? Okay, but remember, this is based on month. right? What we just found was the monthly trend because it's in every 5 months. So a year would be 12 months, right? We want to make sure to use 12 months for that. Okay, so I'm going to plug that into the calculator then. I kept my original amount to try to use that original number. So I'm using the full decimal, 1.148698333. I'm sorry, 8355. And then I'm going to raise that to the 12th. And I get 333,363 users, actually round to 4, since we're talking about people, users in a year. Now, if you use the other equation, the E equation, it does come out a little bit different, a tiny bit off from this number because we're talking about a lot of decimals here. But they're close. And so I'm pretty comfortable that if it was in my open math, they'd accept the answer. But if there's any issues with entering the answers and it like comes out, it's not accepting it, I'll double check to make sure that we haven't rounded so differently from the answer that it's accepting. All right. Okay, the last type of example we'll see is Newton's law of cooling. I like this one. It's kind of fun. And it's something you do see in calculus for anybody who moves into calculus after this. Okay, so the idea is when you leave something that's hotter than the air around it out, it'll cool off. Okay, and that law of cooling actually follows a formula. Here's the formula. If T is the temperature of the surrounding air, I'm sorry, if T is the temperature of the object and T sub S is the temperature of the surrounding air, it follows the formula T of little t equals A e to the KT. So they use E in this growth problem plus T to the S. So it'll get a chance to work with E. So it's using the growth formula, calling R basically K, right? It's that continuous rate of cooling, and TS is the surrounding temperature. Okay, so let's look at an example of this. Cheesecake is taken out of the oven with an ideal internal temperature of 165 degrees Fahrenheit, placed into a 35-degree refrigerator after 10 minutes. It's cooled to 150 degrees. If you have to wait till it cools down to 70 degrees, how long do you need to wait? I love it. This is such a great example, especially when you're hungry for cheesecake. Okay, so since we are working with a refrigerator that is at 35 degrees, that is our surrounding temperature for it. So T sub S is 35. And then the initial temperature is 165. So that's what it starts at. Okay, so let's take our equation here. T of T equals A e to the KT plus T sub S. Let's plug in our T sub S. And initially, when time equals 0, oops, it's 35. This thing is 160 degrees. Sorry, 165 degrees. So I'm going to plug 165 for T, capital T. Little t, our time, is 0 because this is what it is when it first comes out of the oven. It goes into the refrigerator. And then our surrounding temperature is 35. Okay, so this is actually going to allow us, oops, I just realized I switched E and A, to solve for A because that's going to be E to the 0, right? K times 0 is just 0 and E to the 0 is 1. So that's just A times 1, which is just A, which means I could solve for A by just subtracting 35 from both sides. Wow, why am I not writing the 5 there? Who knows? A is going to be 130. Okay, so here we go. We have A now. And now we're interested in how long it has to cool to get to be 70 degrees. Now, before I do that though, my original formula here, here's where I have now. I'm now at the point where I have A and T sub S, but I don't have K. So I still need to find K. And they did give us another piece of information. And the other piece of information they gave us was this. After 10 minutes, the cheesecake is cooled to 150 degrees. So that is the information we're going to use. Okay, so 150 degrees. Ooh, gotta switch to the red pen. Oh, I did. It just was too slow. 150 degrees equals 130, and that's 10 minutes. So keep in mind that T is in minutes in our final answer. Okay, so subtracting 35 from 150, that's going to give me 115. I'm going to write 10K instead of K times 10. Divide by 130 on both sides. Gives me probably a gross decimal. I might just leave it as a fraction. Yeah, it's a gross decimal. So in order to save myself from dealing with rounding, I'll leave it like this. Equals E to the 10K. Okay, now I'm going to take the natural log of both sides, which is really nice with E, because when we take the natural log of E, those two things cancel, and we're just left with the exponent. So natural log of 115 over 30, 130 equals 10K. So K is going to be this number divided by 10. All right, so let's plug that in. Natural log 115 divided by 130, and then all of that divided by 10. I am getting negative 0.0123. 123. So exciting. There's K. So now we need to figure out how long it's going to take to get to 70 degrees. So I'm going to squeeze my work right over here using my new formula. T of T equals 130 e to the negative 0.0123 t plus 35. There's the formula I'm going to use. I want to figure out when this thing is going to equal 70, solving for t. 1, 2, 3. Okay, so 70 minus 35 is going to be 35 itself. Now, for the sake of space, and I apologize about my dog, for the sake of space, I'm going to not show the division, but I'm going to do 35. Actually, no, here. 35 over 130. I'm going to stick with my original idea of leaving it as a fraction. Equals this. When I take the natural log of both sides, that E cancels. So this is the step I'm going to skip. The E cancels, and I'm left with negative 0.0123 t. Okay. So to solve for t, I'm going to divide natural log of 35 over 130 by negative 0.0123. And I end up with t equals 106.6, which is in minutes. So I'll just say 107 minutes, though in hours, that would be, let's see, 1 hour. So 107 minus 60, 1 hour and 47 minutes is how long it would take for this thing to fully cool. But that's okay. I'll leave my answer in minutes. I just realized that green line's going right through it, and that looks tacky. Boop. There we go. All right. And that will be the last example we'll do on logarithm and exponential modeling.